3.2 implicit differentiation, day 2 on this one. So today we will get into still doing the implicit differentiation, but it will be also looking at a higher order derivative getting a second derivative. And there's just a little bit of a trick to it from compared to just doing a first derivative. So here we go. First one is an AP multiple choice question, and this is question number 84, which means that it would be on the with calculator part of the test. And you're going to see that there really is no need for a calculator on this one. And that is true kind of many of the questions that sit in the calculator section of the AP exam. All right, here's my function. If x natural log y equals 2, then dy dx equals. And you're supposed to recognize the fact that you'll need to use implicit differentiation to conduct the derivative on this. I also notice that I've got multiplication going on, so I can see product rule with implicit differentiation. All right, so let's go forward with the product rule. F prime g plus g prime f. I hope this is entering your mind every time you come into doing a derivative as you immediately think of what is the rule for that particular derivative. So I'm going to take the derivative of x, which is 1 multiplied by the second function, natural log y, add with it. Now I've got to get the derivative of natural log y. The derivative of natural log, oh, well, the rule for that is 1 over u times u prime. So I'd have 1 over y times the derivative of y, dy dx. There's the implicit part. Multiplied by the first, and that would be multiplied by x. So this was all natural log work and then multiplied by x. Equals, the derivative of 2 is 0. Make sure you don't mess that one up. A lot of people tend to forget and they put down 2 or whatever number sits on that right side. We've seen most of our equations with a number on the right, but that isn't always the case, but does happen, quite frequently. I'm going to get x over y. I'm just making a line that kind of simplifies out and makes it look pretty, my line prior. So this was just simplifying. Now let's separate. Let's sort this out. And I'm going to keep the dy dx stuff on the left. I just kind of prefer it to be on the left. And it conveniently is already starting on the left. And keep solving. We'll solve for dy dx. So dy dx equals natural log y multiplied by, well, if I were to solve this, what would you do? I would multiply by x over y. I tend to multiply by the reciprocal rather than dividing by x over y, because if you guys divide by x or y over x, I have no guarantees that you know what to do with it once you get it there, right? Dividing by a fraction is like multiplying by its reciprocal, which then I might as well have just multiplied by y over x in the first place. So multiplying by the reciprocal is a very efficient way to solve that equation. And do we have an answer here? Y, natural log y over x. I'm liking C. However, oh goodness, I moved this over because I did not have the answer that was on my answer key. I moved this over, probably talked way too much, and to move that over took a negative, didn't it? So I'm going to end up with a negative natural log. So let's update our answer. It looks like B. Yeah, I made a silly mistake. Example 2. Find the second derivative using implicit differentiation. Exam question number 86, also found in the calculator part of the exam. And they give you x squared plus y squared equals 100. Do you recognize this function? What is that function? It's one that you should know. It is studied when we work with the conic sections. This is the equation of a circle. And its center, do you know what its center is? 0, 0. And its radius would be 10. We can tell all those things, can't we, from that equation? Okay, so let's just say we have this circle, and then they want us to point at the point 6, 8, 6, 8, Let's say it's right there. So I'm going to get the first derivative, and it should have a negative slope. And then I want to go into the second derivative. Yeah, this one's asking for second derivative. I'm like, where did it say second derivative? Right there, right? That is the notation for second derivative. Now, let's take the derivative. First derivative, and label it as such so that you can keep your work straight here. First derivative, it will be implicit because our variables are mixed. And you're probably like, well, I could solve for y very easily on this. Yeah, you could. But then you end up with two branches of an equation, right? Because this really is not a function. A circle doesn't pass the vertical line test. So it takes two equations to write this out, the top half and the bottom half. I wouldn't go there. It'll be quicker and easier just to do implicit differentiation. So derivative of the first term would be 2x dx dx, don't need to write dx dx, plus 2y dy dx equals 0. Let's solve for dy dx, and I'm going to subtract 2x on this one, and I'm going to even put the negative sign down. Learned my lesson last one. Then I'm going to divide by 2y, and I'm going to get dy dx equals negative 2x over negative 2y. Oh, that reduces down to a dy dx of, I'm sorry about the negative down there. Just checked my work. Negative x over y. Yeah, because I was dividing by a positive. Okay, I got my first derivative. Now, how do I get to a second derivative? I take another derivative. We have not worked much with higher ordered derivatives, and strangely enough, it is lesson 3.6 that we get into higher order derivatives, so kind of strange that it hits so much later and then we're doing it ahead of it. Who knows? All right, so I'm going to take from my first derivative. I'm going to work with dy dx. And it appears to me if I want to get to second derivative, which notice the notation, it's kind of different. To do that, I need to employ the quotient rule. So quotient rule coming our way. Derivative of the top would be negative 1 multiplied by the bottom, minus derivative of the bottom would be 1 dy dx, I'll just put dy dx, multiplied by the top, and I'm definitely going to set up a parenthesis because I have that negative and I don't want it to look like subtraction, all over bottom squared. Let's simplify this. We'll have negative y plus x dy dx all over y squared. They want us to evaluate the second derivative at the point 6, 8. Do you see how there's a first derivative embedded in the second derivative? That's often the case. You'll do enough of these, you'll find that that's usually the case. We can do a substitution. Whoops, that bounced back. Let's substitute dy dx in. Or, yeah, the first derivative in. So I'm going to have d squared y over dx squared, which means second derivative. And I got to see my work there. Negative y plus x times, I'm going to substitute in, let's put it in red. You grab a different color and show that substitution. So there's a sub, and it's all over y squared. Okay, that simplifies down a bit. We could simplify it down a lot. I don't think we'll go to the extent of making like denominators and all that good stuff. I just want to get this as negative y minus x squared divided by y squared. You know what, I lied. I'm going to go ahead and simplify this out. I want to make this into not a complex fraction, but rather just a nice fraction. I need to achieve like denominators. So the first term in the numerator needs a denominator of y. And that's going to give me negative y squared minus x squared Common denominator between those two terms is y all over y squared. I can join those denominators together because this is like over 1, multiply by its reciprocal, and voila, we get negative y squared minus x squared. I'm so tempted to pull that negative out front, over y cubed. There is a complete second derivative, simplified as almost as much as we could. I could pull the negative. Now, they asked for dy, second derivative at 6/8, if I'm not mistaken. I just got to plug in the numbers. So we're going to have, I'm going to change my color, the second derivative evaluated at 6/8. And then let's plug in. So we'd have negative 64 minus 36, so that's a convenient number, over y cubed. Y cubed is 8 cubed, getting me negative 100 over 8 cubed is not one that I have in my brain right now. 512. Well, definitely divisible by 4, maybe even more. Let's go by 4. The reason I know is because those last two digits are divisible by 4, so that means that the entire number is divisible by 4. Dividing by 4 gets me a negative 25 over 128, if I'm not mistaken. Yeah. And that should be answer A. Second derivative, implicit, always ends up doing that substitution technique. AP exam free response question. Consider the graph of, and then find dy dx. Okay, so it's going to be an implicit, and then there's multiple questions following that. Well, let's get the first derivative. So piece by piece, 2x plus, not 4, but 4 times 2, 8y dy dx. Anytime my variable is different than the bottom dx, I've got to have that differential statement. And then derivative of 6x is 6 minus 8 dy dx, derivative of y. Plus 0 equals, I think this was a 0, yep, equals 0. Sort things out. So let's keep the dy dx's on one side. Dy dx, if I GCF that, I would have a negative 8 and an 8y. So 8y minus 8 equals 2x goes to the other side through subtraction. 6 is my other lone term. That'll be a minus 6. And I could have dy dx. I'm thinking you guys are probably pretty good with doing all the algebra. I'll divide by 8y minus 8. Shares an 8, so I'm going to factor that out as I do my division. And that would have been 8y minus 8. It reduces, so let's get it reduced. Dy dx equals negative x plus 3 over a 4y minus 4. You probably noticed that when I went after the things in front of my dy dx, it was 8y minus 8. You also probably noticed that I had negative, so I factored out the negative 2 from that. And it just makes it just look a little nicer. Looks great. So part A is done. And let me see if I can make my work all smaller on this because I'm sure we're going to use it. There's part A. Roll out part B. At which points does the graph of the equation have a vertical tangent line? Oh, vertical tangent line, like that. What's the slope of a vertical tangent line? Undefined, right? They have undefined slopes. Which means that I will set the denominator equal to 0. Sweet. So I'm going to pick up my dy dx from the previous part of this question. That has a parenthesis there, doesn't it? Over 4y minus 4. And I want to find where it has vertical tangent lines. So I'm going to set the denominator equal to 0. Pretty easy one to see that y would equal 4. It said at which points does it have a vertical tangent line. Y equals 4 is not a point. It just describes the y value. So we've got to go find the x value. So y equals 4. We will plug in 4, won't we? Let's use a different color here. So we're going to have x squared plus 4 times 4 squared plus 6x minus 8 times 4 plus 9 equals 0. Our original function will help us find the original x value when y is 4. That gives me an x squared plus 16 times 4 is 64 plus a 6x minus a 32 plus a 9. 64 minus 32 is 32 plus 9 is 40, 41. I was just looking at my work and I don't see. I'm not sure I did it right on my work. 4y and y was equal to 4, wasn't it? Okay, so I paused for a moment because I knew something was not calculating right. And you probably noticed my mistake was way back up here. This 8 minus 8, and I factored out an 8. This should be 1. 1 right there, shouldn't it? So make sure you make that adjustment. Oh, darn it. And that means this is a 1, which means this is a 1, which means this is a 1, and that means this is a 1, this is a 1, and this is minus 8, and this is a 4. We're getting there. And this, I knew once I hit 41, this isn't factorable. And most of the time, the AP makes stuff factorable that you don't have to use a quadratic formula. So I knew I needed to start looking around for a mistake. This creates 1. 1 plus 4 is 5. Oh, okay, now we're factorable. So we get into x plus 5. And I'm not going to edit that mistake out and restart this video, because it's good for you to see that you can determine when you've made mistakes a lot of times, right? Things are not flowing very easily there. And I knew something had to have been wrong. So I get x equals -5 and x equals -1 as solutions or zeros of that function. That gives me 2 points where the vertical tangent line occurs. So I'd have -5 comma 4, right, when y is 4, and I'd also have -1, 4. All right, part C. Part C. And I just need to be able to grab that. Here we go. It also wants us to find points. At which points does the graph of the equation have a horizontal tangent line? Horizontal tangent lines look like that. The slope is 0. And how would I find that location? So we know the slope is 0. So set the numerator equal to 0. So now I've got to go find what was my derivative. There was my derivative. dy dx, you probably don't have to rewrite it because it's on your page there maybe. If not, write it down. 4 times y minus 1. And now I'm going to set this equal to 0. If I take negative x plus 3 and set it equal to 0, I get x equals negative 3. Beautiful. Now I've got to go find what is the y value, because once again it asks for the points. So the points means I've got to plug it into my original function, which is way up at the top. Can I pull that? No, can't pull that. All right, what was it? Negative 3? Negative 3. I'm going to erase and work from here. So I'm putting in negative 3 in for x. And hopefully we won't make any mistakes. I shouldn't say we, it was me. This time it looks like we're going to be finding our y value, doesn't it? So I've got a 4y squared minus 8y. 9 plus 9 is 18, cancels away with that. Oh good, this one's even easier, isn't it? Pull a 4y out, GCFing that, leaves me a y minus 2. And we get two locations because there's two factors here. Y equals 0 or y equals 2. And that gives me negative 3 comma 0 and 2 comma 0 as the locations where we have a horizontal tangent line. Nice. Whew, those are hard problems, or they just take a long time. Example 4. This one is under the topic of logarithmic differentiation. And it says, how many of the following derivatives can you answer correctly? Take 1 minute and find it out. Hit pause, give it a shot. Okay, welcome back. Derivative of a constant. I hope you said that this was equal to 0. I hope you said e to the x was equal to e to the x. And I hope this one you used the power rule because it's x raised to 2.718. And that would give us e times x to the e minus 1. Yep. Crazy as that seems. And then the last one, x raised to the x. Never seen one like that, where the variable's in the exponent as well as the base. This one's a problem. And this one, we have to use logarithmic differentiation so that we can bring the exponent down. So we introduce logarithmic differentiation. So what the heck does that mean? Well, let's take our original function, y equals x raised to the x. And let's introduce a log on both sides. You can introduce whatever kind of log you want. I'm going to do a natural log. Okay, so natural log both sides. Then, power rule of logs, not of derivatives, power rule of natural logs would say that I can write this as x natural log of x. Now that's something I can handle. So by doing the log on both sides, we were allowing the x variable to come down and play with the other x's in the equation. Now, take the derivative of both sides. And derivative. This is going to be a product rule on the right. On the left, it's natural log y, so the derivative of natural log y is 1 over u times u prime, which will be a dy dx. So we get 1 over y dy dx. And over on the right side, product rule kicks in, a 1 times a natural log x plus derivative of natural log x is 1 over x times x. Let's just clean up a little bit. 1 over y dy dx equals natural log x plus 1. Solve for dy dx, and we'll have our derivative. Yeah, this was a doozy. So we get dy dx equals, multiply both sides by y, and we can multiply up and we get y equals natural log x plus 1. Done. Now I need to have both the x and y values in order to find that derivative at a location, but that's okay. Or can I write this all in terms of x? If I wanted to convert to all x's, I would just use a substitution. Because I know what y is, so I could say dy dx is equal to, well, y started out as x to the x. So I could put x to the x natural log x plus 1. How would I know if I should go that far? Well, in the AP, sometimes they say express the answer in terms of x, or they'll say in terms of x and y, and that'll be your guiding principle there. All right, I think there's a couple left to go, and this one is going to be quite similar to kind of the one we just did, I think. It's just got 2x up on top. So I'm going to walk through it a little bit more quickly this time. Y equals x to the 2x. Let's natural log both sides. So I get natural log y equals natural log of x raised to the 2x. Natural log y equals 2x natural log of x. Power rule, right? Not of derivatives, just of logs. Next, let's take derivative. Derivative of both sides, this will be a 1 over y dy dx. And then I'm into product rule. 2 natural log x plus 1 over x times 2x. That gives me a 1 over y dy dx equals 2 natural log x plus 2. I don't need to be fancy. Let's go dy dx equals multiply by a y. And we'll have 2 natural log x plus 2. If you want to replace y, you definitely could. X 2 to the x natural log x plus 2. I missed writing a 2 there, sorry. And there's our answer. Oh, that's it. Yay. Okay, so your worksheet is a mixed derivative practice, so it's not going to be all just logarithmic differentiation or even implicit differentiation, because I don't see any implicit going on there. It's just going to be nice, good old power rules and things like that, quotient rules. So it is kind of a nice mixed bag for you. Good luck.